So now that we've seen one basic example, let's talk about trig substitution in general. So in general, there's a table that you can use to determine which substitution you want. If I have something like square root of 4 minus x squared, then I'll use x equals 2 sine theta. If I have something like square root of 4 plus x squared, I'll use something like x equals 2 tangent theta. And if I have something like square root of x squared minus 4, I'll use something like x equals 2 secant theta. Now with each of these, there is a corresponding domain of my inverse and a trig identity that I'll use as I replace whatever's under the square root with something that's trig and squared so that my square root can cancel. So let's look at the example, the integral of 1 over x squared times the square root of x squared plus 4, all in the denominator. So notice I can't use u substitution because although I have something outside the square root, it's not the derivative of the inside. And so u substitution won't work for me, but I could try trig sub. So why don't you do that? Why don't you use the table to figure out which substitution you want and pause the video and get as far as you can with the trig substitution, and then we'll talk about it together. Okay, now that you've had a chance to try this trig sub, let's actually work it together. So we're going to use that x squared plus 4 is under the square root, which means we want to use x equals 2 tan theta as our trig sub. This means that dx is 2 secant squared theta d theta. This also means that my theta is between negative pi over 2 and pi over 2, which we'll use if we need to. And that's going to be my substitution. Now let's go ahead and sub everything in to my integral. So I get the integral of 1 over, see 2 tan theta all squared is 4 tangent squared theta. So I get 4 tangent squared theta plus 4. And dx is 2 secant squared theta d theta. So I replace both x and dx for my substitution. Wow, it looks a lot more complicated. But I know that I want to use the trig identity. Tan squared theta plus 1 is secant squared theta. So let's work this out and see if we can't simplify things algebraically. So I have a 2 and a 4, so I can at least simplify there. So I have a secant squared theta on top. I have a tan squared theta, a 2 tan squared theta on bottom. And I could factor out a 4 and get tan squared theta plus 1, which is the same as secant squared theta. So I can get an integral of secant squared theta over 2 tangent squared theta square root of 4 secant squared theta d theta. And that secant squared theta is coming from my trig identity. Because of this trig substitution and this trig identity, I'm able to rewrite what's under the square root as something I can actually take the square root of. So I get the integral of secant squared theta over 2 tangent squared theta. And now when I take the square root of 4, I get 2. When I take the square root of secant theta, I'm going to have to worry about whether it's positive or negative. So for now, I'll just write it as the absolute value. And now let's think about whether it's positive or negative. So secant theta is the same as 1 over cosine theta, and I'm on negative pi over 2 to pi over 2. Well, cosine theta on negative pi over 2 to pi over 2 is positive, so we're good. So I can ignore those absolute values. I'm positive on this interval. So I get the integral of secant squared theta over 4 tangent squared theta secant theta d theta. Now, of course, I can cancel a secant theta from the top and bottom. So I get the integral of secant theta over 4 tangent squared theta d theta. And now I want to write this in terms of sine and cosine, because maybe something else will cancel. So let's see, secant theta is 1 over cosine theta. Let's pull the 1/4 out front. Tangent squared theta in the denominator is the same as cotangent, or it's cosine squared theta over sine squared theta d theta. So now I actually can cancel a little bit more. My cosine, one of my cosines in top and bottom cancel. And now I can write this as 1/4 cosine theta over sine squared theta d theta. So now that I have these two trig integrals, and it's just cosine and sine, I know the derivative of sine is cosine, I can look for a u substitution and see that if I use u equals sine theta, du is cosine theta d theta, that I can sub in and get 1 over u squared. So I get 1 over u squared du. Take an antiderivative, so that's u to the -2. I add 1 to my exponent and divide by -1. Plus c. Hey, I finally was able to take an antiderivative. 1/4 u to the -1, a -1/4 u to the -1, plus c. Am I done? Well, not quite. I still have a lot of back substituting to do. So first of all, I'm going to sub back in for u. So I get this equals -1/4 times 1 over sine theta plus c. But I actually didn't start with sine theta. I started with x's. I started with x is 2 tangent theta. So let's try to get back to what x is. So if x is 2 tangent theta, then x over 2 is tangent theta, which means I have a right triangle with an angle theta, and my opposite over my adjacent is equal to tangent, so that's x over 2. Meanwhile, my hypotenuse is going to be the square root of x squared plus 4 from the Pythagorean theorem, since I know two sides. And that means that sine theta, which is opposite over hypotenuse, is going to be x over the square root of x squared plus 4. And that's what I get to plug in for sine theta. So I get -1/4 times 1 over x over the square root of x squared plus 4. When I divide by a fraction, I multiply by the reciprocal. So I get -1/4. Square root of x squared plus 4 goes in the top. X goes in the bottom. And I still have a plus c. So I get -1/4. I'm just going to leave the -1/4 out front. I get -1/4 square root of x squared plus 4 over x plus c is the integral of 1 over x squared square root of x squared plus 4 dx. And that's another example for trig substitution.